All right. I think in architecture, since we're going to go as low as we can, we might as well start at the bottom and work our way all the way up. These slides are taken by Dr. Gary Tyson. Just a little caveat, see I cited, see my citation. Can't get me for plagiarism now. All right. We're going to talk about basic processing design. We're going to start with some physics. Warning, I'm going to wave my hands a little because we're not electrical engineers. Is anyone here an EE guy? No EE? Okay, that's fine. Talk about transistors and gates. So there's different levels of abstraction, aka different ways to think of a processor. You could think of it as just solid state physics. You could think of it as just a bunch of conductors, insulators, semiconductors. You could think of it as just a bunch of doped silicon. You could think of it as just a bunch of gates. You could think of it as a bunch of combinational logic with muxes and decoders. But on top of that, you usually have clocks, some type of latches and memory, and different state control, and then processor control. But we're going to start from the beginning with physics. And before that, we'll talk about conductors, because not all of us know what a conductor is. It's a material that permits electrical current to flow easily. I'm going to try to keep my wording correct. Remember, with electricity, there is electrical flow. It has to be a circuit, so the electricity has to flow through a circuit. I've been told that a lot of high school teachers teach it differently. It is a flow. That's what it is. It is a flow, and it has to have a circuit to flow. Conductor allows flow or permits it. Namely, it resists it or has a very low resistance to it. There is no perfect, well, there probably is a perfect conductor somewhere, but everything that we have has a low resistance, and we call it a conductor. An insulator is a poor conductor. It has a very high resistance, so it resists anyone trying to push electricity through to flow. And the example of that is lattice of atoms with strongly held electrons. So a lattice of atoms with many free electrons is a conductor. A lattice of atoms with strongly held electrons is an insulator because it's not going to allow the electrons to flow. A semiconductor is a material that can act like a conductor or an insulator depending on conditions. Variable resistance to current flow depending on how we call it dope it, or what you do to it. Bless you. All right, so we chose silicon, probably because of how absolutely cheap silicon is to get, as well as a couple of properties that are nice about silicon. So this is from the periodic table of elements, 14. What's nice about silicon is that it has 4 electrons on the outer ring that are free electrons that can actually flow from to and from nearby atoms. So if you have a lattice of silicon together, the question is, what is a pure silicon lattice? This is kind of a trick. I'm going to tell you right now it's a semiconductor because it has some free atoms. It doesn't have a lot. It doesn't have 0. It just has some atoms that it's allowed to flow about. So N-type doping, we can increase the conductivity by adding atoms of phosphorus or arsenic to the silicon lattice. They have 1 more electron, which is free of wandering. So if you have phosphorus in the middle and you have your silicon, which is allowed to share the electrons, you have this extra electron chilling, and he can easily move about the lattice. So the electron can easily move about the lattice. What does that make it? A conductor. All right, so if you add phosphorus correctly to your silicon lattice, you're going to get a conductor. P-type doping. Interestingly, we can also improve the conductivity by adding atoms of, was it gallium or boron? They have fewer electrons, which create a hole. Now, this is a little tricky, and it's important to understand the difference because you need to figure out N-type and P-type before a transistor is going to make any sense to you, or a diode. So by having 1 fewer, they create a hole. Holes conduct current by stealing electrons from their neighbor, thus moving the hole. This is called P-type doping, since we have fewer negatively charged electrons. By the way, quick history lesson. We think of electrons as negatively charged because Ben Franklin got it backwards, the flow. And if anyone ever does circuits, the flow is usually the opposite way of the way you draw it. Because, oops, he got it backwards. But that's why we think of electrons as having a negative flow and not a positive, or a negative charge and not a positive charge. So if you add gallium, notice that there's a fewer electron. So it can accept an electron. Think of it almost as sucking or pulling what it can, something to it. So an electron's free to fly right into it. And so that turns it into a conductor as well. All right, kind of understand the difference, at least high level. I know I'm waving my hand. I am waving my hands, by the way. But we're not EE people. So you start with silicon, you add phosphorus or arsenic, gallium and boron, and some metal wires, and boom, you have a processor. Okay? That's all you gotta do. You gotta carefully add phosphorus or arsenic and gallium or boron, put some metal wires onto silicon, and you have yourself a processor. That's one way of thinking how a processor is made. Obviously, that's not very useful for us because we have no idea how we're supposed to add that, but at one level, that's all a processor is. So there's the wafers, which we talked about a little. And then here's an idea of packaging on a chip. This is an older chip, but it helps you understand. You've noticed that when you have a chip, you have little pins. Oh, how many of y'all put together a computer? Not too many? A couple? I need to bring in my show and tell box. Because I keep forgetting people have not seen how you put a chip together. But the idea is you'll have this black rectangle. You have little feet that come out, and those connect to the board, and then you have metal wires that go to your chip or your silicon chip in order to do the processing. All right, and this is actually where we're going to stop before we get into a junction diode, because I'm going to review these slides, so this part hopefully makes a little more sense when we get to it. Before we conclude, make sure you go on GitHub and you email me your GitHub name, and then log into ScrumDo, and you should get, and that's just scrumdo.com. Log in via GitHub, it'll be easier, and then it should give you your ScrumDo username. Make sure you email me both of those, and I'll set you up with both ScrumDo and GitHub, and hopefully next time I can get the internet to work and we can start using ScrumDo from here on out. Okay, that is all for today. Any questions?
Will the slides be on Blackboard?
Yes. Well, not Blackboard. I'm sorry. They'll be on GitHub.
Okay.
GitHub. They'll be on GitHub. And I'll put a link to GitHub, and I guess I'll put it to ScrumDo as well. That way y'all can both get to it. Anything else? All right. Well, that's all for today. This is going to be a great classroom. I will see y'all on Wednesday.